So today let's go back to my vintage multimeter restoration. This is the multimeter from one of my previous videos which I tried to restore with not much success because of its poor condition. The biggest problem was this switch for the current wrenches. Somebody tried to fix it using glue, because the knob was probably slipping on the shaft. So somebody probably put a glue in it to fix it, but he not only glued the knob to the shaft, but also the knob to the front panel, and also the shaft into the switch, and also the screw which is in the knob was glued into the knob basically. He tried to fix a knob slipping on its shaft, but he basically ended up filling the entire switch with glue. He probably put a bucket of glue in it. Now the shaft is completely glued in it and it can't move. And the knob was also glued to the front panel. And when I was trying to separate it, I completely burst this panel. And of course I was probably a bit impatient. Instead of trying to maybe heat it up or using some solvent like acetone, I tried to basically pry the knob off to separate the glue, but I managed to burst it. I glued it back together, but it looks quite crappy, and anyway, the biggest problem is that the shaft is completely glued in the switch and it's completely impossible to make it move, and the switch is basically inherently part of this housing, of this plastic or bakelite box, so I can't just take the switch out and put another switch into it. Those contacts of the switches are basically molded into it. And I also have a feeling that the bridge rectifier in it for the AC ranges is also damaged, and somebody also blown some resistors in it, so instead of restoring this one I decided to use it as a donor of parts, and I will try to restore this one, which is also in a questionable condition. Most of this one seems to be in a good condition, enough for a restoration. All the switches work, they move, no glue in them, as in the other one, and the plastic box or bakelite box is fine, no cracks, no damage, the glass is okay, but there is this broken terminal and the other one is bent. It seems like somebody smashed it, somebody like dropped it on the floor like this, and here is this cover, which the other one is missing. So I have this cover finally, and of course I will also use this box from this broken one, and I can take those terminals and put them into this one. But of course the biggest question is, what the hell is this? Are you seriously kidding me, guys? What's this? It looks like a piece of a coil of wire. It's probably some resistive wire from some current sensing shunt, which works as a low resistance resistor. So somebody probably blown some of its current ranges, and the current sensing resistor basically melted and a piece of it came out, and now it's loose inside of it and it went into this analog meter. So this one is also in a questionable condition. Somebody probably blown some of the ranges of the current meter. So now let's try to test it. So let's try to measure the resistance of the current meter. The highest range seems to be okay. It has a very low resistance. And the other one is 0.8 kilo ohms. It seems blown. And the other ranges as well. So it seems like the 6 amp range has another shunt and the other ranges used this shunt. Even lower ranges probably have some other shunts, but in series with this one, so it's also almost open circuit. And this is the resistance of probably the analog meter, but there is no shunt in parallel to it anymore. But of course I could potentially restore it using the shunt from this one. Now of course the question is the analog meter damaged or not? So let's try to measure some battery, 1.58 volts, and this one shows 1.5, it seems close enough, and the other one 0.5, that's bad. Let's try a 3 volt battery, 3.3 actually, and this one shows about 2 volts, and this one shows 3.2 or 3, it's close enough. This one seems fine, it's just ever so slightly below. Now let's try the 12 volt range using two such batteries about 6 volts, and Nothing. Okay, so it seems that some ranges of the voltmeter are blown. 1.2 volts is 1.2 kilo ohms, that's fine. 6 volts, 6 kilo ohms. But 12 volts, open a circuit, and everything higher than this also open a circuit, so it's blown. The DC voltmeter probably works like this. You switch resistors in series with this analog meter, and the first range works, the second one also works, but the third one doesn't work, the 12 volt range, which means that this resistor is probably blown. And this resistor is also used for all other ranges above it, so they also don't work. So the conclusion is that the resistor for 12 volts is blown, and it also disconnected all higher ranges, and the shunt for 1.2 amp range is also blown, and it also disconnected all lower ranges because those are in series with it. But now, of course, let's take a look in it. To open it, it's necessary to remove the knobs. So let's unscrew them. There is a tiny slotted screw for the knobs, and this one comes off. It's not glued like in the other one. This one also comes off, and finally this one also comes off. And here are the knobs. The knobs have a metal ring molded into them, and this screw to tighten it onto the shaft. The ring looks like this. It's from the broken multimeter, and here's the screw. Now let's unscrew this cover, which also has some schematics on it. There is a strange screw. Let's unscrew it. Now let's open this. And here you can see the switches, which are the same as in the other one. And some other screws which are still sealed. There is still the original seal on them. It has never been opened. That's nice. But unfortunately I have to break the seal now. It doesn't work. I have to fix it. And here's my kit helping me, of course. So let's unscrew the screws. And a surprise. A box of shunts. And those shunts are the same as in the other one. And none of them is blown. The blown one has to be from the other side. So let's further open it using another 6 screws. Here, 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 and here. And those screws are 3 different lengths to make it less confusing. And now it maybe opens. Yes, it does. And that's it. Or actually 2 different lengths. The other one has 3 different lengths. And here you can see the internals, which are more or less the same as in the other one. And here you can see the coils of resistive wires in the current meter, and one end of the blown shunt is probably this wire, and the other end of it is this terminal here. Let's try to put another in it. And here is the remain of the blown shunt, as you can see. So let's put another in it from this donor of parts. In the other one, this shunt looks nice. So I've desoldered the current sensing shunt from here and put it here. So now let's see if the current meter is fixed now. It's the highest range, very low resistance. Still a very low resistance. Still a low resistance. Going slightly up as I go to the more sensitive ranges, which is right. 12 ohms, 47 ohms, and 100 ohms for the most sensitive range, which is only 1.2 milliamps. And it's so sensitive that it shows the current of my resistance meter. So now let's test it. This is the highest range and connected to my bench power supply with a current limit set to 3 amps, and it actually shows 3 amps on its DC scale. And this is 1 amp on the highest range, and on this range it is It actually shows a little bit less than it should, but this is probably because the solder kind of reduces the resistance of the current sensing shunt. Now roughly 0.3 amps, and it shows a bit less than it should. Now let's try 100 milliamps, and it is also slightly less than it should be, but okay. Now I noticed that when I leave it sitting for a while, it's then more accurate, but then it's slowly drifting down. So there is probably some temperature drift. Now let's try 30 milliamps. It's very close. And now 10 milliamps. This one is quite accurate. 3 milliamps, also very accurate. And the lowest range at 1.2 milliamps, super accurate. So the DC current meter works fine. But the AC current ranges all show about 20% less than they should. And there is also a blown resistor in the voltage section. In this multimeter there is a 6 kilo ohm resistor, but the same resistor in this one is open circuit. So let's try to swap it. It's this resistor here. So now it's desoldered, and does it come out? Yes. And those resistors are basically slided onto some pins going from the contacts of the switch. Those pins or wires go from those contacts. And the other one comes out, the blown one. I can see a loose end. So let's put the good one in it from the other multimeter. So now it's soldered into place. So now the resistance of the multimeter is what it should be. 1.2, 6, 12 kilo ohms, 30, 60, 120, 300, and 600 kilo ohms. Now it seems to work quite accurately. 10 volts on 12 volt range works fine. Now 30 volt range, very accurate. 60 volt range, also very accurate. 120 volt range, also fine. 300 volt range also seems fine, even though it doesn't show much now. But my bench power supply is only up to 30 volts. And 600 volt range also seems to work. It only shows 3 divisions. All DC ranges seem to work very nice. Now let's try AC voltage from a tiny transformer. 11 volts, and this one shows 8.6 volts. It shows about 20% less. This is the 12 volt range. Now let's try 30 volt range. Now it shows about 9 volts. Now 33 volts from a transformer, and it shows 27 volts. On a 60 volt range, and 120 volt range, 28 volts. And now the 300 and 600 volt ranges. Should I stick it in mains? Now let's plug it in mains. Does it explode? It doesn't. The voltage is about 240 volts, and it shows 190. And the 600 volt range shows 200 volts. All AC ranges show a bit less, AC current and AC voltage. Is the bridge rectifier damaged, or is there some special resistor just for AC ranges which is damaged? I also noticed that the AC scales of those two multimeters are different. They are kind of shifted or compressed at the beginning, but each of them a different way. The beginning is shifted and compressed to compensate for the voltage drop of the bridge rectifier, which means that each bridge rectifier probably has a different voltage drop in those multimeters. They are not exactly the same version. This one has a resistor here, which is missing here, and this one has a resistor here, which is missing here. But the resistors I swapped were the same, luckily. Also, the covers are a bit different. This one is even, this one is rough. They are different versions. And this one has a lower series number, so it's probably older. And this looks like a capacitor to me, but it says 180 kilo ohms, so it has to be a resistor. But this one is a capacitor. Isn't it damaged? I desoldered one end of it, and does it have some leakage current? Seems nice. and it says 4 nanofarads, and it is actually 2.77, so it has lost about 1/3 of its capacitance. And the other one has the same capacitor in it. Should I swap it? And this capacitor in the other multimeter is 8.1 nano. It's more than double of what it should be. Those capacitors seem to deteriorate over time. And its resistance, it's open circuit, it's fine, but the capacitance of it is completely drifted. I tried to put another capacitor in it, but it doesn't seem to have any effect at all. And on the internet I found this website with the description and schematic of this amazing device, and it's a scan from 1956, and back then this multimeter was already quite common, it says. And here's the picture of it. It also shows the bearings of the analog meter with jewels and some needles. And it even describes how to rewind the coil of the analog meter, which is completely crazy. It says it has 240 turns of a wire which is 0.06 millimeters diameter. And this graph shows the diameter of the wire versus the maximum tension in grams you can pull the wire when winding it. It basically says how to disassemble the bearings of the analog meter, how to rewind it. You have to dissolve some resin, unwind it, rewind it, dip it in some resin and reassemble the mechanism. And this one shows the play of the bearings. Bloody hell, those multimeters were probably quite expensive back then. So people would go through the ordeal of rewinding the analog meter instead of buying a new one. And here's the full schematic of it, also with a diagram of the AC-DC current voltage switch. And here it talks about the bridge rectifier, which is actually a bridge rectifier, but both AC pins are connected with each other, so it actually works as just two diodes, or two parallel pairs of diodes. And here's the simplified schematic of the AC voltage meter, and this potentiometer actually is the switch which switches 8 different resistors. So it basically is a resistive divider with this resistor, and the voltage from the divider goes into this rectification circuit with two diodes and some resistors. So one half cycle goes through this diode and through the meter and this resistor here into here, and also some current goes through the diode and this resistor, so it bypasses the meter. And the other half cycle goes through those diodes and the meter, but also the other half of the current goes through the diodes and the resistor, so only half of the current goes through the analog meter. And there is also this capacitor which I showed you, and this capacitor, it says it's to compensate it for higher frequencies. It can also measure AC voltages at higher frequencies, and this capacitor probably compensates its lower sensitivity for the higher frequencies. So it measures accurately at audible frequencies. And here's the DC voltmeter simplified schematic, which is quite simple. And here's the AC current simplified schematic. And this potentiometer actually is the switch with multiple shunts. And again, the rectifier is basically two diodes and two resistors, and only half of the current goes through the meter. And the DC current meter is super simple. It also tells the current and the power the voltmeter draws at the different ranges. And it also says how much voltage the current meter drops and how much power it dissipates. It also describes how to rewind the resistive coils. And some vintage pictures of the internals. And it says the accuracy is 1% for DC current and voltage, 1.5% for AC current or voltage at 50 Hz. And it says 50 cycles per second, the old way, but it's 50 Hz. And it's 3.5% up to 10 kHz frequency. And it says that most of the failures are because of overloading it, which is completely right. And it says that the analog meter can get stuck because of iron dust and you should remove it using a needle. It even says how to rebuild the bearings under a microscope, straightening the frame of the analog meter here. Here it also says how to balance the analog meter system. It even says how to magnetize the magnet or partially demagnetize it during a calibration. You can magnetize it by putting a wire through it and connecting it to a high DC current from a car battery or a DC welder, or you can also partially demagnetize it by applying a variable AC voltage or current or AC magnetic field. This is absolutely amazing. It's completely crazy how much people would do back then to repair it. Nobody would go through such an ordeal nowadays. It must have been bloody expensive back then. And the bridge rectifier in it is copper oxide. I was thinking it's germanium or selenium, but it's actually copper oxide and the reverse voltage of it is just 2 volts. Which is quite a low voltage, but it also probably has a very low voltage drop. But if the maximum reverse voltage of the rectifier was just 2 volts, it must have been very easy to blow it, of course. If you apply too much voltage to the rectifier, it may not completely destroy it, but it can change its characteristics. And this is probably the reason why my AC ranges show about 20% less than they should. Some older version actually had a bridge rectifier, not just 2 diodes. And here you can see the full schematic in a better quality, and there is a link to this website in the description. To calibrate the AC ranges, there is probably this resistor R4, which applies to both AC voltage and AC current, but doesn't apply to DC ranges. This resistor is basically in series with this bridge circuitry in both cases. So I could change the resistor R4 to calibrate the AC voltage ranges, and then I could maybe use this resistor R1 to calibrate the AC current. This one only applies to AC current and no other functions. And this picture even shows the positions of all components. The resistor R4 is here and the resistor R1 is here. So let's try to recalibrate it. Here is resistor R4 and resistor R1. The manual basically says change resistor R4 after replacing the bridge rectifier. So I tried putting various resistors in parallel to it to get the reading a little bit up, but it turns out that I have to put a short circuit on it to get it close to the right reading. Now it shows about 9 volts and it should be 11, and when I put a short circuit on it, it's about 10.5 or almost 11. The error was about 20% and now it's less than 5%, so let's call it roughly calibrated. Now let's try a different voltage range and a mains voltage. The actual voltage is 239 volts and it shows about 230 on its 600 volt range. And on the 300 volt range it actually shows 240, which is quite accurate. Now let's try AC current. At 1 amp it shows about 0.9 amps. Well, but the resistor R1 for the calibration of AC current ranges is already such a low resistance that there is almost no headroom to get it more up. So it seems like the rectifier could have some damage in it. Now the question is, should I try to swap it using this rectifier from the other multimeter? But it's probably a bad idea because in this multimeter the AC ranges didn't work at all. But anyway, let's call this multimeter kind of restored. The DC ranges are quite accurate, the AC voltage ranges are no more than 5% error, and the AC current ranges are probably maybe close to 10% error, but all ranges of DC and AC current and voltage kind of work. So it's restored to the extent possible, and of course it's not possible to replace this copper oxide rectifier with anything modern. Now let's replace this broken terminal and this bent terminal, and that's it. So I've put the terminals on it from the other one and it's more or less restored. Now let's put the knobs on it and that's it. And of course here's my cat helping me. And now the knobs are back in place, and it also has a very nice box from the other multimeter. So this is Wild, and see you in my next videos, and thanks to all of my patrons on Patreon. I really appreciate your support. And I also plan to take a look at this brake fluid tester, which was donated to me, so thank you for your donation, and let's take a look at it in one of my future videos.